Introduction to Project 3. The objective of Project 3 was to build and code a robot to accomplish certain tasks. The scenario for this project required the team to build a prototype Mars rover that could perform various delivery functions such as transporting cargo, following a given path, which was indicated by a line on the floor, whether it be dotted or straight line, traveling over obstacles, as well as controlling speed. The image in the bottom right shows the track for the course. Project management. Our roles were a recorder, and the recorder created meeting minutes and made sure everything was included in the design notebook. Next up was a coder who created the framework of the code, tested it, and troubleshooted it. Next up is a builder who was responsible for constructing the macro, a meeting coordinator and timekeeper who created agendas before each meeting and made sure we completed all the tasks allotted, an encourager, gatekeeper, who made sure everyone's ideas were heard and that all ideas were considered fully. Lastly, a devil's advocate, who had the responsibility of making sure our ideas would function as intended. Multiple people could assume multiple roles at once. For example, multiple people were coders for this project, and one person could be both a builder and recorder in a single meeting. The screenshot on the right is the main tool we use to figure out when to hold meetings, a website called When to Meet, where each individual would fill in the time slots that they were available, and the very dark green spots would indicate where times where the entire group was available. The picture at the bottom of the slide is the top part of the work breakdown structure, showing our initial concept of the general categories and the tasks associated with each goal. Next up is the Gantt chart. This is our initial conception of a work schedule. The first third of the work period was spent brainstorming and making decisions for prototypes of the macro. The second third was spent building and coding the macro. The final third was reserved for testing and revision to solve issues that would inevitably come up, necessitating changes to the original design. Documentation and reporting was completed throughout the work period. There were some deviations in this original work schedule. The main deviation was in the blending of building and coding and testing and revision.
In the design process, the team created a detailed engineering specification chart detailing the requirements of the macro, such as the volume of the cargo hold, speed, and sensing capabilities. The team's initial brainstorming method was to spend 5 minutes having each team member write and/or draw out their ideas for each category in question. The picture below is an example of a team member's brainstorming drawings for the overall robot layout. Finally, the team created a decision matrix for each of the 3 main decisions: wheel type, drivetrain design, and cargo mechanism design. Each decision matrix was based on ratings due to the lack of ability to gather enough data within the given work period for the project. However, each rating for each decision was based on proper background research. The picture to the right is the team's initial perception of a functional block diagram of the macro system that visualizes the system's main functions and their codependence. The first prototype of the system was based on decisions made with the decision matrices, which involved 4 wheels, a rear-wheel drive, and a conveyor belt cargo system. However, this system had a few issues that were discovered through initial testing. This brings us to the second prototype. The change from 4 wheels to only 2 wheels in the front was made due to friction between the wheels and the ground. Because of this friction, turning using different positive and negative speeds for the left and right wheels was virtually impossible. By using 2 wheels instead and having a more sled-like base, the macro could spin in place, reducing the turning radius to practically 0. The change from rear-wheel drive to front-wheel drive was necessitated by the fact that the sled at the front would be unable to go over the obstacles. However, this version of the prototype kept the conveyor belt cargo mechanism. The final prototype kept the 2-wheel sled design with the front-wheel drive. The major change was the changing of the cargo mechanism. During the presentation of competency, it was revealed that cargo would not stay on the conveyor belt while the macro was moving or attempting to go over an obstacle. The cargo gate mechanism solved these issues by creating a holding space large enough to secure the cargo while it was being transported. In addition, this design made it simpler to transfer systems, as a motor in the same position and orientation was sufficient to power the gate.
We designed our software with ease of modularization and editing in mind. Each function or task the macro must perform is encased in separate functions, defined at the beginning of the code file, or have its own compact and concise block of code in the main function. The picture below is an example of such a block of code, here used for the ultrasonic sensor. Our initial conception of a software framework is depicted in the segment of flowchart to the left. The code would start with an ignition loop where it was constantly receiving input from the touch sensor. The touch sensor was used as an ignition button. As soon as it was pressed, the code exited that loop and entered the loop of the main code. The main code had several segments, and each could overwrite the others to determine the speed of the macro and/or call on functions to perform different tasks. Therefore, the order that the sensor's code appeared in was critical. The first sensor to be tried was the line finder. Flowchart block A, not shown, described its function. If a black line was sensed, the macro would simply move forward along the black line. However, if a white line was sensed, the macro would enter a function for finding the line again, which involved turning right and then left in order to search its surroundings. The next sensor was the ultrasonic sensor at block B, which could overwrite the line finder's go forward mandate if an obstacle was obstructing the robot's path. Following that, at block C was the IMU. This used a counter variable to determine the path the macro would take. Its options were to turn right, for example, at a branch to the cargo drop-off zone, go straight to ignore the branching line, unload at the drop-off zone, and reload at the landing zone. These functions would interrupt the main code, run the assigned functions, and then return to the main code to continue navigation. The final function at block D was another touch sensor ignition system, this time acting as an emergency stop button. If this was pressed at any time, the code would break out of a sensing loop, stop the macro, and end the run. The only major change associated with software was the switch from the Hall sensor to the IMU. This necessitated a reworking of any code associated with sensing magnets so that the macro could properly react to the magnetic beacons. Next, the speed and time settings within functions such as finding a line, unloading cargo, and turning at a beacon were being constantly changed throughout the manufacturing process as the team received increasing access to materials such as test tracks and sample magnets. Finally, the team added variables that controlled the speed and magnet sensing responses. The cargo variable controlled the speed of the macro since it moved much slower with cargo loaded. This variable toggled between 1 and 0 for cargo loaded and not loaded, respectively, and made sure that the speed of the macro was the same, regardless of if it was loaded or not. The counter variable controlled decisions regarding what function to perform at a magnet. It incremented by 1 every time a beacon was sensed, and the code made decisions based on its value.
Positive and negative attributes of the prototype. The final prototype had 3 main negative attributes, which were the location of the magnet sensor, the line finding function, and the tilted wheels. The IMU sensor was located roughly 3.5 centimeters above the ground, which made it too far away from the magnet that it needed to sense. In the picture, you can see the macro continuing down the line when it should have turned at the X behind it where a magnet is located. To fix this, the IMU sensor needs to move closer down to the ground. Next, the macro had an inefficient line finding function that took 6 seconds to try and find a line. When the line sensor did not see a black line, the macro could turn to the right about 90 degrees, then to the left 180 degrees, then back to the right 90 degrees, and then slightly move forward. This takes an unnecessarily long time. A more efficient way of doing this would be to use 2 line finders on either side of the black line and alter the speeds when one of the line finders sees the black line. Finally, the macro's wheels would tilt outward, which caused problems with driving straight and with the line finder sensing the black line. The left wheel turns out 7 degrees from vertical and the right wheel turns out 3 degrees from vertical. This causes the macro to drift towards the right when it should be driving in a straight line. To fix this, the wheels would need to be supported from the outside as well as the inside. positive attributes. The final prototype has 4 main positive attributes. First of all, macro is very compact. It is only 38 by 17 by 14 centimeters. Having a compact prototype makes it more transportable. Next, the prototype is able to navigate rough terrain. From trial runs and data collection, the robot has been able to go up a hill 100% of the time and can maneuver over obstacles 95% of the time. The macro struggles with getting over some large obstacles, but can consistently get over smaller ones. The macro can also achieve desired speeds easily. The prototype passed the speed test 100% of the time during practice and during the final demonstration. Finally, the prototype has an effective cargo mechanism. The macro held and unloaded cargo 96% of the time during testing. The gate mechanism holds the cargo in place and turns into a ramp to release the cargo smoothly.
At our demonstration, we discovered that our IMU sensor was set up or calibrated incorrectly. As a result, we were unable to sense most of the magnetic beacons on the demonstration course. In addition, our line finding function was not optimized for the dimensions of the track, so the macro failed to navigate tighter turns effectively. However, the macro successfully crossed the obstacle at the start of the track while carrying cargo, and successfully crossed the hill during the presentation of competency. The loaded cargo went on and came off the cargo hold of the macro as intended and did not fall off during the macro's motion. Finally, the macro is highly optimized for speed control and is able to run at any speed the user wishes.
Areas for improvement. There were a few design decisions that did not work out as planned. The function for finding a line was very slow and inefficient. In addition, some speeds and timings were still off at the time of the demonstration. The current location of the IMU is ineffective, as it cannot see a magnet from that location. Finally, the macro is very front-loaded, with a heavy Raspberry Pi holder, Raspberry Pi, and rechargeable battery pack situated directly above and between the wheels. This is likely a cause of the distortion in the wheel angles. Based on these faulty design decisions, there are several hypothetical revisions. Lowering and/or recalibrating the IMU sensor is necessary to be able to effectively sense a magnetic field. Further testing with test tracks and magnets would be optimal. Our current proposed solution for the tilting wheels is to support them from both sides instead of only from the inside. This solution eliminates a need to reposition the heavy Raspberry Pi materials while still addressing the problem. Finally, in order to solve the inefficiency of the line finder program, we could use 2 line finders instead of 1. This would require rewriting some user-defined functions in the code that would make line sensing and finding more effective and efficient.